welcome back to our video series on regression analysis. In our last video, we looked at the calculation of our least squares estimates, and we determined how to calculate a confidence interval and how to conduct a hypothesis test. We dealt with our distance and finds data, and we're going to continue to do so in this video. And at the end of the video, we'll look at the topics in R that we've discussed in the video. One of the things that we do need to be wary of is called extrapolation. This is predicting beyond the range of our X data. What do we mean by this? I might, if I predict outside the bounds of my data, come up with values that make no sense, such as negative weight, negative height, negative speed. These values make no sense when I try to predict. So I need to stay within the bounds of my X data if I'm going to predict. This is one of the reasons our intercept is typically not interpreted. What about our variation? Remember, we're running a linear regression and we're trying to find a model for the data. We're trying to find our line of best fit. And more than likely, we're going to miss some of our data with this estimated line. So we need to determine how much of our variation we can explain using this line of best fit. Well, our total variability in Y is n minus 1 times the variation in Y, S squared Y. But the total variation in Y when we use our regression line is n minus 2 times our mean square error. So we've got some leftover variation. And our proportion of this unexplained variation is n minus 2 times the mean squared error over n minus 1 times the variance in Y. Well, since this is our proportion of unexplained variation, we'd like to find the proportion of variation we can explain. So if we simply subtract the proportion of unexplained variation from 1, this gives us the proportion of explainable variation. And we can use our correlation to actually calculate this. So remember, R is our correlation coefficient, and it measures the strength of the relationship between X and Y. R squared is going to equal 1 minus the unexplained proportion of variation. Therefore, if we simply square the correlation value, we will get the proportion of variability in Y that is explained by X. But how is R squared defined? Well, if we recall, R, our correlation, is bounded between negative 1 and 1. This means R squared is bounded between 0 and 1. R squared is simply interpreted as the percent of variability in Y that is explained by X. Now, R squared value must be interpreted. A high R squared value, this implies more variations explained. That implies a good line. It suggests that we are explaining more variability using our regression line. A low R squared value implies little variation is explained, and so this means that this line is a poor fit. So in this case, our R value is 0.9631, and so R squared is 0.9275. So approximately 92.76% of the variability in Y is explained by X, and we can see that as the trend goes up and as our line runs through the trend, there's very little variability among our residuals. We've got small residuals. Here we have a few large residuals, but overall, the residuals are very small, as opposed to this particular plot. Here our correlation is 0.1002, and so R squared is 0.01005. And notice we have this large variability among our residuals. And so approximately 1% of the variability in Y is explained by X. We're not explaining much. This is a poor fit. Well, what defines a good R squared? Well, it depends on our discipline. Engineers, physicists, mathematicians, statisticians prefer an R squared greater than 0.9. Biologists, on the other hand, may feel that an R squared greater than 0.4 is good, and then social scientists may feel that an R squared greater than 0.2 is good. Other items we need to look for are called influential points and outliers. Influential points are one point that completely changes the analysis. So our influential points can change the slope of the line. Notice in this graph, our line comes through right here. However, by adding 1 point, our line changed completely. We can see that the slope is now changed. The residuals are much higher. Outliers, these exist in the vertical direction. Here we can see there are several large outliers. So how do we determine if we do have outliers? Well, we want to use our residuals. So what are our residuals? Our residuals is simply yi minus y hat I, where y hat I is beta hat 0 plus beta 1 hat xi. Now, one thing we can do to determine if we've got outliers is construct a box plot of the residuals to detect our outliers. Notice, here's the box plot of the residuals, and I've got several outliers up here. I've got several outliers down here. So clearly this residual box plot has outliers. But we should also construct a scatter plot of the residuals and check for patterns. we'd like to see random scatter around 0. Here, I've got a good residual plot. There's no pattern. I've got random scatter around 0. Here, I do have a pattern. Notice, I have a quadratic pattern in my residuals. So now, instead of having y hat equals beta 0 hat plus beta 1 hat times xi, I might have y hat equals beta 0 hat plus beta 1 hat xi plus beta 2 hat xi squared. And so I need to add a squared term to my model. Here I also have a residual plot that has a pattern, but notice this has a V-shaped pattern. And this is typical of what's called non-constant variance. So now I have non-constant variance among my values, and so I get this V-shaped pattern, and it can run going the way this is going, where it's going fanning out from 0, or you may see this fanning towards this 0 line. So in either case, if I've got a V-shaped pattern, I've got non-constant variance. Well, what happens if I have residual scatter plots which indicate nonlinearity? When we have data that is nonlinear, we can use certain transformations to help fix that. One of our most popular forms includes the natural log of y equals beta 0 plus beta 1 x. Now, here we can see we have data that is exponentially distributed. So if we take the natural log of y, notice this becomes linear. Another example of natural log transformation can be seen here. Again, I've got exponentially distributed data. However, if I take the natural log of y and set it equal to beta 0 plus beta 1x, I get a linear line. But then I'm left with the question, how do I interpret beta 1? And the answer is I can interpret beta 1, but I can't interpret e to the beta 1. So if I have to do this natural log of y transformation, then once I get my values for my estimates, I then need to exponentiate everything out so that I can get y back into its original form. And so I take e to the natural log of y, that gives me y, and that's going to equal e to the beta 0 plus beta 1x. For every 1 unit increase in x, we expect to see an e to the beta 1 times increase in y in this case. This is a multiplicative effect now, it's not additive. Another popular transformation is when I have to take the natural log of y and the natural log of x. And so I get natural log of y equals beta 0 plus beta 1 times the natural log of x. And so if I exponentiate this out after I've got my estimates, what I get is y equals e to the beta 0 times x to the beta 1. Here, beta 1 is simply the power of a single variable, single x variable. Another transformation is the square root of y equals beta 0 plus beta 1 xi. Now, once I do this and I get my estimates, I now have to square things out. And so I get yi equals beta 0 plus beta 1 xi quantity squared. Another popular transformation that we're going to look at deals with proportions. And so here, I've got a continuous x variable. However, I do not have a continuous y variable. This is either a success or a failure. So if y is 1, it's a success. If y is 0, it's a failure. And we'd like to model this data, but we can't do this with a straight line because our y values are proportions. So we're going to use what's called the logistic regression transformation. And so we're going to take the natural log of the proportion of successes over the proportion of failures, and that's going to equal beta 0 plus beta 1 times xi. And we will discuss more on this in our next video. Let's take a look at how we can do some of these things in R. We're going to focus on our variability, and we're going to focus on our residual plots. Okay, so let's recall we were dealing with our distance and find data. And so I want to take the correlation of the distance and finds, and we found that that was 0.432418. But I'd like to know how much variability in finds can be explained by distance. And so if I simply square this correlation, I get 0.1869713. Now, I could also use my summary YLM statement. Recall, in our last video, we saw that this summary statement gives us our estimates, our standard errors, our t-values, and our probabilities. But it gives us a few other things. And one of the things it gives us is this multiple r squared value. Notice, multiple r squared, 0.187. There's no need to currently worry about adjusted r squared. This is for multiple linear regression, so there's no need to even use this. Also, notice, our S statistic in this case, 0.2451, is the same as our t statistic for our distance, 0.245. However, let's concentrate on the multiple r squared, 0.187. What did we say we got when we did our squared correlation value? 0.18697. So 0.187. And so what we would say is that 18.69% of the variability in finds can be explained by distance. Now let's also take a look at checking our residuals. First, I want to plot our data. So here's our data. Notice this could be an influential observation. And I'm going to add this command AB line with our YLM. That's what we called our function. And I'm going to add a color of red because I want to add the regression line, our estimated regression line, and here it is. Now notice we've got these residuals, and we'd like to check these. So I want to plot these residuals, and so what I'm going to do is plot resid of my function YLM. This will give me my residual plot, and here it is. I'm going to put in an AB line statement here so we can see how these residual values revolve around 0. Notice there really is no V pattern. There is no quadratic pattern. And so it does look as though this is a good residual plot. But how about outliers? Do we have any outliers in our plots? Now let's take a box plot of our values. And notice there are no outliers in our box plot. And so this does look like it's going to be a good line. Okay, that's it for this video. In our next video, we will begin discussing logistic regression. See you then.